Hello, it's Keith here, and this is lesson 66 of the platform-specific series of my 6502 assembly programming tutorials. We're looking at the PC Engine today, and we're looking at my ChibiTracks music player, which we looked at before. What we're going to do is we're going to add the playing of music to the previous Mintile example. Mintile is a little graphics engine. You can see it running here. We can move our character around the screen, and we can flip our character around. It's just a simple graphics engine, but we're now adding sound while keeping the animation going, and that requires interrupts. So what we're going to look at is how to get interrupts working on the PC Engine. So let's go straight over to our code and let's take a peek. Okay, so here is the code that we've got today. So this is the file we're looking at. It's PC Engine Mintile with sound. Now, as with the normal 6502, we have a block at the F6 onwards range, which defines the various vectors. Now, the PC Engine isn't a true 6502. It's a 6280. It's modified 6502 with some extra functions and things. So it does have a different block, and the purposes are different. Now, on the regular 6502, the FFFE and FFFF bytes would define the reset vector, and they don't actually do that on this system, at least not necessarily at the address we're looking at here. You see, the PC Engine has a memory mapper, and so in most cases it's the logical addresses that define the vectors that occur, and that's true of the interrupt handlers. But the vector for the reset is actually at the physical address, and so we have that actually at this address here. This is the address that will actually end up functioning as the reset vector, and so we've got a reset vector of E000 there. But the other interrupts will actually occur at the address that we've got here, which we will page in to the logical address range at the top of the address space. And so we're actually defining the same interrupt handler for all of the interrupts. We're going to work out what interrupt occurred and deal with it. We're actually only using VBlank in this case, but we've got a non-maskable interrupt here. We've got the timer. We've got IRQ1, which is any video interrupt, and the only one we're going to be using is VBlank. And we've got IRQ2, which is also the break interrupt, and it's only this one here, this IRQ1, that we're actually interested in today. Now, we've got our interrupt handler here, but we'll have a look at that in just a moment. First, we'll just take a quick peek and see what it takes to actually get the interrupts running. Okay, let's take a look. Now, there's two things we need to do to turn the interrupts on. The first thing is we need to tell the video hardware to actually start creating the VBlank interrupts. Now, the interrupts are defined by the bottom 4 bits of the register 5 within the video register. So we're selecting register 5 here, and we're writing the bottom 8 bits here, and you can see that the bottom 4 bits, we've set the top one to 1 and the others to 0. Now, each of these is a different purpose. Basically, the top bit of those is VBlank. The next one is a scanline match. We can cause an interrupt at a certain line number. We have sprite overflow, which generally means that there's more than 16 sprites on a line. That is the limit of the drawing. And we have a collision interrupt that we can use. But of course, it's only the VBlank one we actually want today. So we're setting that top bit there. This one here, we're setting that to 1, and that will cause the VBlank interrupt to occur. However, that just makes the video hardware cause the interrupt. We actually need to allow the interrupt to occur, and that is done with port 1402. Now, this is actually called the interrupt disable, and so a value 1 within this register will actually turn the interrupts off. So we want to turn one of the interrupts on. We want to turn on interrupt IRQ1, and that is the middle bit there. So that 0 in between the two ones there is turning on the VBlank interrupt. If I set that to 1 and I run again, well, you can hear we now have no sound at all. There's no sound playing. Equally, if we leave that as a 0, but we now change this to 0, well, now the IRQ will occur, but we have no sound because the video hardware isn't generating the interrupt. So we need to do both of those things to get the interrupt working. So that's all we need now. Once we've got our interrupt handler pointed to in the vectors at the top of the address space, our interrupt handler will now occur on VBlank. Now, what we're going to do here is we're going to check a couple of things. Firstly, we're going to check what interrupt actually occurred, just in case we've got other interrupts enabled. So what we're doing here is we're loading in from port 1403. That byte will define which of the interrupts actually occurred. Now, because of the way we've set this up, actually, it can only be VBlank that has occurred. But just to check, we are checking the other two interrupts. And if either of those is 1, the bits here will match the ones when we turn the interrupt on. If either of them is 1, we're going to skip down to interrupt handler not VBlank down here. We then want to clear those interrupts because the interrupts would potentially fire again otherwise. And all we do is we set a bit to 1 and write a value back to 1403, and the bits would match here. So I'm simply sending a value of 255, which is going to stop every single interrupt from occurring. It just clear all those interrupts. So that's what we're doing there. However, the VBlank is actually different because that is being generated by the video hardware. We need to tell the video hardware that we've processed the interrupt. And so what we're doing here is we're reading in the VDC status register here, and that will clear the interrupt, and so that will stop the interrupt from occurring again. Now after that, what we're doing is we're running the ChibiTracks play routine, which updates the playing. Now this uses a variety of 0-page pairs, and you can see I'm backing them all up here. They match Z80 registers because this was ported from the Z80. It also uses the accumulator and the X and Y registers, and you can see we're just backing up those here. We're returning with an RTI, and so that will automatically restore the flags from the stack, so we don't need to do that. But as I say, the other stuff we do need to do. Now, just as a point of example, if I disable this line here, we are now no longer clearing the interrupt on the video hardware. So if I run again now, you can hear we've got a god-awful noise, and that is because the interrupt is firing over and over again, and the music is playing at full speed, and now we can't move our player because none of the processing time is actually being released for the rest of the code. It's all being used by the interrupts. So that's just something that caught me out when I was trying to write this, so I just thought I'd let you know about it. Now, what about ChibiTracks then, the music player? Well, basically, it's a pretty simple music player. It uses my platform-specific Chibi Sound Pro driver. So basically, there's one sound driver for each system, and so this will include the one for the PC Engine. And then ChibiTracks itself uses these fractioning routines to calculate the in-between notes. There's some shared modules I may decide to use again. So we need to include all of these files here to allow the ChibiTracks to play. We also need a song, so we've got one here. This is a binary file. You can also use ASM files. The ChibiTracker actually uses ASM files as its raw data format, and they can be assembled with a Z80 assembler. So in theory, you could assemble one here as well. But we're using a binary file here today. The player and the platform-specific driver need about 128 bytes for their function. So we're defining some memory, Chibi Sound RAM here, and we are going to use some of those parameters for the song settings. So we're setting the song offset, the song base, and a few other internal parameters within the song file that will be initialized by the code itself. We do have a couple of options we can choose to enable or not. Allow relocation allows the binary music file to be loaded to a different address to the one it was compiled to with the ChibiTracker. This allows if you don't do that, it makes the file a little bit faster to play and the player a little bit smaller. But it means that if you compiled it to be loaded at memory address C000, that's the only address it will play from correctly. Allow relocation means there's a recalculation, it will play from any address. I would suggest you have that enabled. Allow speed change is something different. When each line of the song will have a certain delay until the next line is read in. These are then multiplied by the song speed, and this is the final playing speed. Allow speed change allows that song speed to work. You can multiply the song speed into the binary file as you export, and then you can disable this. That will result in a faster playback, smaller player. However, it doesn't allow you to change the speed, and that does cause a problem with a system like this. Now, the song itself was designed to be played on a 50 Hz system. However, the system we're using today is a 60 Hz system, so the song will play a little bit fast. Now, it's up to you if you consider that to be a problem or not, but I find it a little bit frustrating. That's the song playing at the default speed for this system, and that is a little bit too fast. However, because we have enabled allow speed change, we can override the song speed and change it from, I think it's 5 by default, we can change it to 6, and that slows it down a little bit. That allows the song to be played a little bit slower, and it sounds more like it should on this 60 Hz system. So that's a benefit of song speed. Of course, you can also do things like make the music play faster as the player runs out of life. And if you want to make the game feel a bit more pressured, that's another thing you could do with that. It's another entirely optional, but it's a potentially useful function depending on if you're doing multi-platform for different frequencies and you don't want to re-export the song multiple times. Now, how do we actually use the player? Well, it's pretty straightforward. We need to initialize the platform-specific driver with Chibi Sound Pro in it. We load the address of the song to the song base values, the 16-bit value there. we then run ChibiTracks start song. That will then initialize all of the other values, and then in this case I'm overriding the song speed, but that is entirely optional. All of these other values are all read in by that initialization of the song there. So those are all set up, but things like the memory address of the instrument list within the internal file, they're all loaded in automatically by that initialization routine, and that's all it takes. So there we go. As I always say, you can go to my website, download the source code, the build script. You're welcome to use all this in anything you want. The main purpose of today's tutorial was just to show how the interrupt handlers work on the PC Engine, because I say it's not quite a 6502, and a lot of these systems, while they all have similar functionality, sometimes you need to do things like today to get the hardware-specific hardware to output the interrupts in the way that we want, and to clear those interrupts, of course. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.